Hey guys, so I'm going to be going through the AS 2018 paper for statistics today. Just the statistics part, the mechanics part is in a separate video. My year 12s did this as one of their mock exams, so I think this should be helpful for you. Okay, so we're going to start off by reading question 1. It says, a company is introducing a job evaluation scheme. Points, which are measured in X, will be awarded to each job based on the qualifications and skills needed and the level of responsibility. So basically, the more points, the more qualified or the more responsible the job is. So more points, harder the job. The pay in Y pounds will then be allocated to each job according to the number of points awarded. And you'd expect the more points that you've been awarded, the more money that you should get paid. Before the scheme is introduced, a random sample of 8 employees was taken, and the linear regression equation of pay on points was y equals 4.5x minus 47. So as soon as you see this phrase, linear regression, what we should probably be thinking is, this is to do with our correlation and regression topic. Just so it's always good to know what kind of chapter we might be working from here. Okay, it first of all says, describe the type of correlation between the points and pay. Well, if this is the equation of the line of best fit, this thing is telling me about the gradient of the line, and it's clearly a positive gradient line of best fit, and so a positive gradient line of best fit must mean that it is a positive correlation. And again, it just kind of makes sense. The more responsible your job is, the more money that you should be earning. Part B of the question says, give an interpretation of the gradient of this regression line. Well, if x is the number of points and y is the amount of pay, this means that every time x increases by 1 point, then the pay would have increased by 4.5 or £4.50. And that's really what gradient means. Gradient means that every time you go 1 across in the x direction, that you're going to be going however much in the y direction. So a gradient of 3x means going 1 across in x, you move 3 up in y. So just like this, you move 1 point up and you go £4.50 up. So the interpretation of the gradient means for every additional 1 point, which I'm just going to say is x, an extra £4.50, what did it say, is allocated to the job. An extra £4.50 is allocated to the job. Okay. And part C of the question says, explain why this model might not be appropriate for all jobs in the company. Well, if you just have a look at the equation and just sort of think to yourself, when would this not make any sense? Okay, so imagine that you were going to get paid, and let's just say that you had 1 point or maybe 10 points. If you had 1 point, it would be 4.5 times 1, take away 47, which is going to be a negative amount that is going to be paid, which doesn't make any sense. I'm going to pick a different. I'm going to say if x was equal to 10, you would have 4.5 times 10 minus 47. So let's say for some points, pay becomes negative. E.g., and you can pick any value as long as it's between 1 and 11. E.g., if x equals 10, y equals minus 2, which doesn't make sense. Okay, let's just review the mark scheme and see kind of the phrases that they might have used here. So for question 1, you do have to say positive. You don't have to say correlation, but positive is the minimum thing they're looking for. Every point gives £4.50 more on pay. You could have just said 4.5 as well, but we wouldn't have done that really. And you can also say every 10 points could be £45, as long as there's something about that comparison. And they've said for any points less than 11, it would give a pay which is less than 0, which is ridiculous. We just picked a particular one here. You didn't have to say that it was less than a particular thing. We just could have just given a particular thing. They've also suggested a sample size of 8 may not be very representative to cover all jobs as well. So that's something else that they picked up on. Okay, question 2. A factory buys 10% of its components from supplier A, 30% from B, and the rest from supplier C. Well, as soon as I see that, I probably want to write something down. A does 10%, B does 30%, well that's 40%, so C must be the rest, which must be 60%. That's 100%, take away 10 and take away 30. It is known that 6% of the components it buys are faulty, and that's the components that it buys from all of the different places, from A, from B, and from C. Of the components bought from supplier A, 9% are faulty. Of the components bought from supplier B, 3% are faulty. Find the percentage of components bought from supplier C that are faulty. Well, this sounds like a kind of probability type question. So I want to try and draw on some of those skills that we've got from probability. There are many, many ways of answering this. Just the way that my brain visualizes this is as a tree diagram. So I know that there are 3 different suppliers that we've got here. We've got supplier A, supplier B, and supplier C. And then from those suppliers, they are either faulty, which I'm going to say with F, or not faulty, which I'm just going to say as F dash. Faulty or not faulty, faulty or not faulty. And this just helps us, our brains, to visualize what's going on here. So let's just label some of the bits. 10% of them are from supplier A. It's going to change it to a decimal. 30% from supplier B, which means 60% are from supplier C. Now, the ones that are faulty from A are 9%. Don't write that as 0.9, that's obviously 0.09. And if you wanted to, we could say not faulty, but I don't think we're interested in that at the moment. And from B, it says 3% of them are faulty. We want to find out how many of them are faulty from supplier C. So we can either call this X, but I might call it P because it's a probability. And we know that if you were going to try and find all of the ways of it being faulty, which would be going along here and along here, that's going to be where you find some of the faulty. Along here and here, that would give you B and faulty, and along here and along here. Those 3 ways added together are all going to be equal to 6%, because that's how many of them are faulty in total. So all of those 3 branches are going to be equal to 0.06. Well, the first branch that we have is 0.1 multiplied by 0.09. The second branch that contributes to this 0.06 is 0.3 multiplied by 0.03. And our last branch is 0.6 multiplied by P. Now, all we need to do is just solve this equation. So I'm just going to do some of that calculating here. So it's 0.1 times 0.09 plus 0.3 times 0.03. So here we've got 0.018 plus 0.6p equals 0.06. Obviously, you could do this all in the calculator all at once if you wanted to. So let's do 0.06, take away 0.018. So that's 0.042. And then I'm going to divide both sides by 0.6, and we come up with that P is equal to 0.07. So find the percentage of components bought from supplier C that are faulty. So we should actually change that back to a percentage and say 7% of components from C are faulty. That's part A of the question. Now, part B of the question says that a component is selected at random. Explain why the event the component was bought from supplier B is not statistically independent from the event the component is faulty. Now, actually, this is in the formula book, statistical independence, but it's not in the AS section. It's actually in the A-level section. So this is the A-level section of the formula book. Let's see if I can just show you that at the top of one of the pages. So this is the pure maths bit of the A-level. If I just go down to the statistics section though, you will see in the probability bit, it says 4 independent events A and B. These are from year 2. This is the one that we're going to look for here. So it says the probability of A and B is equal to the probability of A multiplied by the probability of B if they are independent. So basically when you multiply them, they should be equal to the probability of them both happening. Let's try it then. So it looks like we've got these 2 different things. We've got the probability that it is bought from supplier B, and the probability it's bought from supplier B is 0.3. The probability that it is faulty, the component is faulty, well, 6% of them are faulty. We worked that out, we were told that earlier, so that's 0.06. And the probability that it is from B and it is faulty, B and faulty is 0.3 times 0.03. Which is 0.009. So let's work it out. The probability of B multiplied by the probability of F. This is like this bit. Let's actually see what that is going to be. So it's going to be 0.3 times 0.06. That is 0.018. And that is not equal to 0.009. So these events are not independent. If they were independent, then multiplying these two would be the same as giving you this one here, but it's not the same, so they are not independent. And this working that we have over here is enough to convince us. So let's just have a look at what's in the mark scheme for this one. So question 2, the tree diagram or some other method gives you the method mark. You then get an accuracy mark for coming up with this kind of statement, and then a third mark for solving it, but it does have to say 7% because it's asked for percentage. And then for part B, they've worked out the probability of B and F, which we actually did as well, and then the probability of B multiplied by the probability of F, and they're clearly not the same as each other. They're not equal, so they are not independent. That's exactly what we've got there. I think that's quite a lot of work for 1 mark, personally. Okay, question 3. Nasir is playing a game with 2 friends. The game is designed to be a game of chance so that the probability of Nasir winning each game is 1/3. Nasir and his friends play the game 15 times. Find the probability that Nasir wins exactly 2 games and more than 5 games. Well, Stats does this. It never really tells you what the topic is, but we should recognize that he is playing a fixed number of games. The probability is fixed. There's only 2 outcomes because he could either win or lose. And what's the last thing? And they're independent of each other. The way that he plays this game, they're not going to be conditional. They're going to be independent. So all of this makes me think that it's going to be binomial distribution. Okay. So we're going to do this here. Let's figure some of these bits out. So first of all, I always like to write down the test statistic. Let x be the number of games that Nasir wins. And for part 1, we're going to try and find out what's the probability he wins exactly 2 games. Well, x is going to be distributed binomially. He is playing the game 15 times and the probability is 1/3. So we want to say, what is the probability that x is equal to 2? Now this is just a job of, do you know how to use your calculator? So I'm just going to go into my menu and my statistics bit. It's maybe a bit different if you have a class whiz. And I'm going to take myself to binomial distribution. I'm actually going to use the probability distribution rather than the cumulative distribution because I just want the probability of it being equal to something. So I want x to be equal to 2. I've got 15 trials and the probability is 1/3 or 1 divided by 3. Hit equals on my calculator and I get 0.0599 and I have done that to 4 decimal places. Part 2 of the question says I want to know the probability that it is more than 5. That means that x cannot be equal to 5, it needs to be more than 5. Now whenever I think about this, I always start thinking in my head, okay, well what would more than 5 be? It would be 6, 7, 8, 9, etc. So I have removed everything which is 5 or less. So I have removed everything which is less than or equal to 5. That's why I have the less than or equal to 5, because I want to get 5 or below. So I'm now going to just put in my calculator, going to the other version. I'm not going to the probability distribution, I'm going to the cumulative distribution. And this time I want my upper limit to be 5, and I come up with 0.61837183 blah 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 blah. So I'm just going to do that subtraction. 1 minus 0.61837183. I'm going to give it to 4 decimal places, 0.3816. Okay. Question B, it says that Nasir claims he has a method to help him win more than 1/3 of the game. So he thinks he's cracked it. He thinks he knows how to play the game better. To test this claim, the three of them played the game again 32 times, and Nasir won 16 of these games. Stating your hypotheses clearly, test Nasir's claim at the 5% level of significance. Okay, before you even start a hypothesis test, I always like to look at this beginning bit and say, what is Nasir thinking? Well, they've played the game 32 times, and he's won 16 of them. And 16 is half of 32. So he's actually been winning half the games, 50% of the games, which is more than a third. So that's why he's got this idea in his head. So let's start off with our actual, what our hypothesis test looks like. So the null hypothesis is that he's wrong, and actually the probability is still 1/3. But the alternative hypothesis is that he thinks it's going to be more than 1/3. So the probability is more than 1/3. And this time we're going to say, let x be the number of games Nasir wins. I always like to write out the test statistic. And we're going to assume that h0 is true. In other words, that x has been binomially distributed, but this time it's not 15 games. They're playing it 32 times, and we're going to assume that it's the probability of it being a third. So we want to see, what is the probability that Nasir plays this game and he wins 16 games or more? And the reason I'm saying 16 or more is because he's already gone, we're looking for 16 or more extreme, and the direction of how extreme it would be going to more than that. It's already above what we would expect it to be. A third of 32, we'd expect maybe about 10 or 11 wins. He's won 16, which is pretty extreme, so we want there to be 16 or above. Now 16 or above means we want 16, 17, 18. In other words, we're going to remove everything which is 15 or below. Hence me doing 1 minus the probability that x is less than or equal to 15. Okay, that's just there to kind of help me think about what it's going to be on this side. So that's going to be 1 minus the probability of x being less than or equal to 15. So you're going to stay in the cumulative one, but you need to make sure that you've changed the number of trials now to 32 trials, and I want it to be between 0 and 15. So I get 1 minus the probability of that, which is 0.9623466, blah, blah, blah. So let's just work this out. It's going to be significant if it's a rare thing to happen. 1 minus 0.9623466. And I'm going to give this to 4 decimal places, 0.0377. And that's 4 decimal places. Now, this is really rare for it to have happened. It's only a 3% chance that he would have got 16 or more. And this is less than 5%. 3% is less than 5%. So, enough evidence. This is a bit saying it is less than 5%. So there is enough evidence to reject H0. This supports... Why have I put an exclamation? Why have I put an apostrophe in there? This supports Nasir's claim that, what did he say? That he can win more than 1/3 of the games, that he can win more than 1/3. Okay, let's check where the mark scheme comes from. You really need to make sure you do put it in context of the question. If you don't put it in context of the question, you don't get this last mark that you have here, okay? So, let n be the number of games that he wins. So you have to write down how it's distributed. That's one of the marks. You then get these 2 marks for just using the calculator correctly. Did we get that 0.3816? Yeah, we did. Okay, so for the hypothesis test, you need to write down the null and the alternative for a mark. You then need to say the test statistic and say the distribution of what it would look like, which we did. You then get 1 mark for actually just working out this probability that we have here, which we've got just a little bit more rounded, but that's fine. And we said it's less than 0.05. And you do need to say there is enough evidence to reject the null hypothesis, so there is evidence to support Nasir's claim. You get 1 mark and it has to have that bit in there, okay? The bits that are in brackets aren't necessary, but these bits are necessary that we have. Just leave that there in case you wanted to see any more detail of this bit. This is with critical regions if you wanted to use that, but I don't think we need to. Okay, we've got question 4 and 5, so we're nearly there. This time it is a large data set question. As soon as we see this word Camborne, as soon as we see about that town. Helen is studying the daily mean wind speed for Camborne using the large data set from 1987. The data for 1 month are summarised in table 1 below. Calculate the mean and calculate the standard deviation for this data and state the units. Okay, NA means that the data is not available. It doesn't mean 0, so we just can't use this at all. Now, A and B doesn't really require you to do any kind of math, it just requires you being able to type it into your calculator. So I've already typed mine in. I have a graphics calculator, so if you have a class whiz, maybe someone can show you how to do this. But I've got it typed in. Hopefully you can see that I've got the numbers down here. And once you've got them typed in with the wind speed down one column and the frequency on the other, all you then need to do is just go to work out what those variables are. So it's a one variable calculation. And immediately what it tells me by just getting these summary statistics for part A is that the mean, which I can just say is x bar, they called it x? I don't even need to call it x actually. Let's just not write that at all. So the mean wind speed is 10.2, and that is knots. You don't have to give the units for that one because it wants the units for the second one. And part B, the standard deviation, this one mean comes up like this on the calculator. The standard deviation comes up like this when you look at it. So the standard deviation, you can just see it from your calculator, is 3.17, and that's, make sure we put the units before I do my rounding, 3.17, and you need to know this, the wind speed is measured in knots, and that's to 2 decimal places. I'm going to show you some summary of the large data set in just a second. Okay, the means and standard deviations of the daily mean wind speed for the other months from the large data set for Camborne in 1987 are given in table 2 below. The data are not in month order, so it's not going like January, February, March, April, May, it's just any, they've muddled them up to confuse you. Using your knowledge of the large data set, suggest giving a reason which month had a mean of 11.57. So if you think about it, the mean here is clearly the highest of all of these ones. So this means that in this month, it was pretty windy. When is it windy from the large data set? You need to know this, but they're actually quite generous. They just kind of let you have a mark if you can explain some of these things. So for part C, you should know it was particularly windy in October in 1987. However, they would accept for one of the marks, for both of the marks, sorry, if you said September as well. I'm going to show you the mark scheme in just a second. Giving a reason. So the month I would suggest is October, because it was particularly windy. In that month. Or you could say something like autumn has windy months. I'll show you in a second, you don't have to have October, there are other things that they would accept as well. So for part D, it says the data for these months are summarised in the box plots on the opposite page, which I've got about coming up. They are not in month order or in the same order as in table 2, so they're muddled up again. State the meaning of the asterisk symbol on some of the box plots, and suggest giving your reasons which of the months in table 2 is most likely to be summarised in the box plot marked Y. So let's have a look at these box plots. These are the asterisks that we're talking about, and these actually represent outliers. So I'm just going to write that down. The meaning of this are outliers. And part 2, which one is going to be box plot Y? Which month do we think it's going to be? So, things we need to look at. It looks like it has a low median when you compare it to the other box plots. So, the low median suggests a low mean, because they're related to each other. They're not going to be exactly the same, but they're going to be related to each other. Another thing that we might look at is that the standard deviation, or the range of the box plot, is actually quite wide. So the range is larger, suggesting a larger standard deviation. And actually, if we look for one that's got a low mean and a kind of a larger standard deviation, looks like ones that have got a low mean are these ones, so it can't be E. But this one's got a small standard deviation, so it could actually be B or C or D. They would accept any of these three answers if you give the reasons. I mean, it's crazy. They make you think there's one answer, but it is just a suggestion. So I'm going to suggest for this one, this suggests it could be B. I'm just going to go with B. Either of any B, C, or D would be accepted. So let's have a look at the mark scheme for this. Okay, these were easy. These were just from the calculator, and you get a mark for saying knots. So they've suggested October because it's the windiest month in autumn, or it's the month of the hurricane. There's actually a hurricane in that month, and I'm going to show you that in just a second. This is outliers. Here we have to have low median, so low mean, and you need to have big range or interquartile range, so larger standard deviation. But if we look in the notes here, we've got a lot of things for these bits about the large data set. So you can either choose October, but you could also pick September. That would have given you the mark. And just to say that it's windier in autumn, and you get the second mark. So even if you've got, even if you said September, you also could have got one of the marks just for saying any month between September and March because that it is windy in autumn or winter. So just be sensible, just have a guess and don't leave something blank for this. And here, look, they've said you can choose B, C, or D. So just a quick bit from this thing that I found online about the large data set. Things you might want to notice here is the UK Great Storm. So October 1987 had very high wind speed, which made us think that that one was going to be October. And the other thing that we needed to know about is for the wind is, where's wind? Here, wind is measured in knots. And also the NA means that the reading is not available. I just found this from someone's Google Drive. It's from, I think, mathsmutt.co.uk. So if you do want to see any of those things from that person, thank you to them. Okay, last question, we're nearly there, is a probability distribution question. So it says a biased spinner can only land on the numbers 1, 2, 3, or 4. The random variable x represents the number that the spinner lands on after a single spin. The probability that x is equal to r is equal to the probability that x is equal to r plus 2 for r equals 1 and 2. That just suddenly was like, what are they talking about? That seems like something I've never seen before. But you just need to keep calm in these kind of exams and think, okay, well, why don't I just look at this information they've given me and look at this information they've given me and see what it tells me. So they've said the probability that x is equal to r is equal to the probability that x is equal to r plus 2. And they've said that r is equal to 1 and r is equal to 2. So let's start off. If r is equal to 1, the probability that x is equal to 1 is equal to the probability that x is equal to 3. Okay, that's great. It's now just saying the chances it lands on 1 and 3 is the same. Now, if r is equal to 2, we get the probability that x is equal to 2 is equal to the probability that x is equal to 4. Okay, so the probability of 2 and 4 are the same. They've told us the probability of getting a 2 on this spinner is 0.35. So I'm going to draw a table. My variables I can get are 1, 2, 3, and 4. And the probability that my discrete variable is that, well, 2, they've just told me is 0.35. And 4, I know is the same as that, is 0.35. These are the same probabilities as each other. So if these add up to 0.7, I will do 1, take away 0.7, and I will divide it by 2, which is 0.15. So these probabilities must be 0.15 because they have to add up to 1. Whoops, those aren't ones, those are meant to be lines on my table to separate them, but I'm making it a bit confusing. So this says, find the complete probability distribution of x. This is the probability distribution of x that we have here. We've said what numbers you can get and what probabilities that they have. Only 2 marks. Ambro spins the spinner 60 times. Find the probability that more than half of the spins land on the number 4. Give your answer to 3 significant figures. So again, this feels like they've put another binomial question in because they're doing it a lot of times now. So let's say, let x be, let's not do x, we've already done x, let's keep it a bit different. Let y be the number of times landing on 4. So that must mean that y is binomially distributed. They're doing it 60 times, and the probability of it landing on a 4 is 0.35. And we want to find out the probability that it is more than half of the spins. That means it has to be greater than half, more than 30 spins. Now, more than 30 means like 31, 32, 33, okay? So we want to get rid of everything that is 30 or less. Hence me writing y is less than or equal to 30. I don't need this bit anymore. And it wants it to 3 significant figures. So I'm going to go back to my calculator. I'm going to go to the distribution. And I want it to be the cumulative distribution. So I want the lower to be 0, the upper to be 30. I'm doing 60 trials, and the probability is 0.35. So it's 1 minus 0.994101. Let's just switch to do that subtraction. 1 minus 0.99411101. And I'm going to give it to 3 significant figures. So it's in standard form, so that's 0.0058899. Let's round that to 3 significant figures. 0.00589. Okay. This is the weirdest part of the whole exam, but again, just trust what you're doing, do the maths, and it will work out. The random variable y equals 12 over x. And we want to find out the probability of this inequality. Well, that looks like weird to me. However, they've told me what y is. So y minus x being less than or equal to 4, I want to do something. I want to change it all to x. So I'm going to replace the y with 12 over x minus x is less than or equal to 4. So I've got an inequality here. I'm going to multiply everything by, does it say y minus x? Yeah, y minus x. I'm going to multiply everything here by x to get rid of this. So when I multiply this by x, I get 12. When I multiply this by x, I get x squared. And when I multiply this by x, I get 4x. Okay, well, I'm not sure where this is going to go, but I'm just going to solve this like it was a quadratic inequality. So I'll put the x squared on this side, I've got the 4x on this side, and then I've got minus 12. Now, your class whizzes can actually solve inequalities and give you the answers straight away, but I'm going to just do this like a sketch. This actually factorizes to x plus 6, x minus 2, so it means it crosses when x equals 2 or when x equals minus 6. So there's my minus 6, there's my 2, and I want it to be greater than 0. So I'm actually interested in this section or this section. So either x is greater than or equal to 2, or x is less than or equal to minus 6. So the question wanted me to find out the probability that y minus x is less than or equal to 4. But that's the same as the probability that x is greater than or equal to 2, or x is less than or equal to 6. Minus 6, sorry. However, there's no minus 6 on the spinner, so that's just not even going to be included. So all we need to do is look at the probabilities that x is greater than 2 from our table, greater than or equal to 2, which is this probability, and this probability here. So it's 0.35. That's the probability of it being equal to 2. That's the probability of it being equal to 3. And that's the probability of it being equal to 4. This adds up to 0.85. A weird question, but just trust the idea of maths, substituting things in, and just using all the techniques that we have so far from pure maths. Okay, let's just very, very quickly look at the last section that we've got here, which is our mark scheme. So we came up with this table that we have here. And then we came up with this correct answer, knowing it was a binomial. You do need to say that it is the binomial distribution, they just used A instead. And then this section down here, which again is coming up with the idea of a quadratic inequality, and then recognizing that x is greater than or equal to 2, which is these three probabilities added together. I hope that's been helpful for you guys, and I will speak to you soon.